All right, so sorry I'm not in today, guys. Something came up, but here we are. We're going to finish our notes. So you remember yesterday we took notes on we took properties on rules of transformations. We had that whole table that kind of described the different transformations for us. So what we're going to do now is we're going to take a look at a graph or at a function. We're actually going to describe how the function has been transformed and sketch a graph of it. So this first one, we're looking at 1/3 of the absolute value of x minus 2. That is our new function. So before we do this, we want to kind of start with identifying what the parent function would be, or the original function, so then we can identify what transformations happened. Well, the thing that sticks out to me is this absolute value sign. So that tells me that the original function in its basic form was just the absolute value of x. So I'm going to go ahead and write that. I'm going to identify the original function. Original function is the absolute value of x. Okay, so now that I know what the original function is, I can identify the different transformations. So looking from left to right, I'm going to start with this 1/3. Well, the 1/3 is on the outside of the original function, which means that it would be a vertical stretch or a vertical compression, something of that matter. Well, since 1/3 is less than 1, that tells me it's a vertical compression. So the 1/3 represents a vertical compression by 1/3. Okay. And then the next one I want to try to identify is what the -2 is, what that represents. Just trying to make my box smaller. It's not going to work out for me today. So, you guys can really hear the rain now, can't you? All right, so next I'm going to, should probably spell compression right. I'm just on a roll. There we go. All right, so next we're going to try to identify what the -2 is. Well, the -2, that's going to represent a horizontal shift because it's on the inside of the function, and this is to the right. So horizontal shift right 2 units. And so there's a couple of ways you could sketch the graph of this, but I know the absolute value function is just a v, so I'm going to start with just graphing the original function. And the reason why I do that is because since I know what all of these things mean, I can just perform that transformation directly. So I'm going to make a v, because the absolute value function is pretty easy. It just keeps going there, and then it keeps going like that way. And then obviously it's going out to infinity. So that's the original function. That's the absolute value function. Now, I'm starting with the shift 2 units right. Or actually, let's start with the vertical compression. So the vertical compression means that it's getting smaller, which means that it looks like it's actually being squashed, and by a factor of 1/3. And so obviously we don't really like multiplying by fractions, but if I do the vertical compression, then 0, 0 starts at the same, but 1 is like at 1/3, 2 is at 2/3, and then 3 ends up being at 1. So it's physically getting shorter. So this is what the vertical compression does, is it just really takes it and it's like sticking a big book on it. It smashes it down. So if the vertical compression, this graph became this guy. And of course I can keep sticking it out a little bit more. Well, now it's just creating a piece. But obviously we're going to pretend like there's little arrows on here that point off to infinity. I'm not going to draw them. All right, and then, so that takes care of the vertical compression. And then now we got the horizontal shift to the right 2 units. And so then I'm going to do that in green. So then my final figure is I'm taking this guy now, the one that I just shrunk, and I'm moving it to the right 2 units. So there, and then 1, 2, 3. Here, 1, 2, 3. So there we go. So basically, this black guy became the green guy, and the green guy is my final answer. Because this figure right here has been compressed by 1/3 and shifted right 2 units. So let's take a look at another one. On this one, we're looking at the -3 times the square root of x minus 1. So same thing, we want to identify the parent function or the original function. So the original function of this guy, oops, probably use the right tool. The original function of this guy is going to be the square root of x, and I gotta use the equation tool for that. Sorry if you guys can hear the rain. I know it's not. Should be square root. Let's see if this actually works. Sometimes it doesn't. There we go. All right. So the original function is square root of x. I hate having these multiples, so original. All right, so now that we know the original function, let's figure out what each of these pieces mean. So the first thing I got is that negative sign on the outside. So even though it looks like it's negative 3, remember the negative by itself is its own transformation. So if I start out with just identifying what the negative represents, don't do that to me. All right, the negative represents a reflection over the x-axis. Okay. And then the next thing that we're looking at is going to be, oh my gosh, can't commit, is the 3. Well, the 3 on the outside of the function, which means that we're looking at something vertical. And this one is going to be a vertical stretch because 3 is bigger than 1. Stretch by 3. So this time it's going to get taller. And then finally, our last function, oh my lord. Our last thing, we'll do it in red so that way, it's kind of bothering me that the last one was in green. But we'll do it in red so that way you know, like, this is the end. Red is, we're working at the minus 1. And if you guys remember the minus 1, since it's on the outside of the function, this is vertical, and it's a vertical shift down 1 unit. Hey, Julia, can we turn that down? Sorry, guys. Go watch that somewhere else, please. All right, so now let's begin. So again, just like last time, I'm going to start with graphing the parent function, the square root of x. And bear with me because this is going to be a curve, and I suck at curves. So we got square root of x. Oh, okay. Shoot, I did something wrong. I did, but I was off to a good start. All right, so I know the square root of 4 is 2, so I'm going to just try to end up over there using the best curve that I can do. And this time we will do an arrow. So that's the square root, the original function that we were given. And now I'm going to start performing this transformation. So the first one I'm going to do is that reflection over the x-axis. So when I reflect it over the x-axis, it's actually kind of cool. It just kind of goes from the same spot. So it going from 0, 0 stays there. 1, 1 is now 1, negative 1. And then the other point that I have that's defined as 4, 2 is now 4, negative 2. So we reflect over the x-axis, the x value stays the same, and the y changes. And if you guys remember back from your earlier days, didn't want to do that. The reflection basically just flips it over the axis. So there we go. This has been flipped over the axis. Pretend like it matches perfectly. So it takes care of the reflection. The next one that we're looking at is that vertical stretch by a factor of 3. Now what this means is that it's basically becoming 3 times taller. So my first point's still at 0, 0, because 0 times 3 is 0. But the next one, 1, 3, 1, 1, 1, negative 1 would become 1, negative 3. And then, actually, we're going to make that a thicker dot so I can actually see what I'm doing here. If I can't see it, you might be able to see it, but if I can't see it, that's not good. There we go. And then the last one we had at 4, 3. That's going 4, 2. That's going to be at 2 times 3 is negative 6. There we go. So now it's starting to look like that. So it's getting thicker. Well, let's actually, you know what? We're going to go back to making it smaller. I just want to be able to see the dots. That's all. Okay, So now we can see that it's been stretched. It's 3 times bigger now. All right, and then finally, we got to just take this whole yellow thing and we're going to shift it down 1 unit. So now it's down 1, went from 0, 0 to 0, negative 1. This one's going to go from 1, negative 3 to 1, negative 4. And then this guy is going to go from 4, negative 6 to 4, negative 7, which is obviously not on there. All right, and the red guy is my final graph. So that's how you sketch the function. And just remember sketch is just like a rough draft. And so obviously you can check it by like what I used to do just to make sure I was kind of like identifying the transformations correctly. And especially since, you know, those horizontal crunches and compressions and stretches are weird. It doesn't hurt to graph it using like Desmos or your graphing calculator, just so you can make sure that your sketch does match up. It's a good strategy. So the next one, now we're going to write an equation for each transformation. And this time we're given an original function. So this is like part of a function. It's not a whole function, but we're just like pretending like this. Well, we're given that this is f of x, and I just want to say how it's been changed by writing an equation. And so before I can write an equation, I just need to identify, well, how has it changed? So if I look here, this is my original function, and this is my new function. So how has it changed from here to here? Well, the first thing that I notice is that it's upside down. And upside down tells me that it's a reflection of some sort. And since it's been flipped over the x-axis instead of the y, that's going to tell me that's a reflection over the x-axis. So I'm just going to write that. Reflection over x-axis. And I can check this because you see my point is still at negative 2, 0. So if it was reflected over the x-axis, it's going to be at the same spot. But then if I check at the next point, which was at negative 1, well, now it's at negative 1, positive 1, which just means that that y value has changed. So that right there is actually, that's truly what signals to me that it was just a reflection and not a translation, not a an extension, or sorry, a stretch or anything like that. Because if it was a stretch, then one of these, this coordinate especially, would be changed, but it's not. It's in the exact same spot. So it's proportional. It's the same, just flipped over. So this is a reflection over the x-axis, which means the function is, we'll call it f prime of x this time. Just because it's the, after the transformation, it's going to be equal to negative f of x. And so this time we're just leaving, we're not given an equation to mess with, so we're just going to leave it in function notation. B is still looking at how this guy right here compares to the original, not the previous graph, to the original. So looking at the original, this one looks like it's been flipped, right? Because it's just kind of doing a weird thing. But it's almost like it's been flipped twice, right? But it hasn't. So notice that so this was, first of all, so reflected over the x-axis, it would end up here, right? But if we change it around and flip it over the y-axis, well, then that really turns this guy right here, and it's just basically making it look like it's backwards. So basically this guy, but upside down. So this one I would say has 2 reflections, because if it was reflected over the y-axis, and we'll draw it over here. So it's reflected over the y-axis, and then it becomes this, which is really kind of flipping over. But then if I reflect it again, so we're starting to get what we want, but if I reflect it again over the x-axis, then now it's, this guy's here, but this guy becomes there, and this guy becomes there. So that's starting to give me more of the shape. So it looks like this guy was reflected over the x and the y-axis. So I have 2 things that happens: reflected over the x and y-axis. However, that's not it, because notice that this graph right here is significantly taller than this graph over here. And I'm going to go ahead and erase this so we can go back to seeing the original graph. So this tells me, since it's being stretched, that it's obviously, well, it's being stretched. And so, because it's getting taller. And so this tells me that it's a vertical stretch. And remember, vertical stretches are on the outside of the function. So now I just need to figure out, well, how much has it been vertically stretched? And so what I'm going to look at is not the point 0, 0. I'm going to look at this point, negative 1, 1, and see how it grew over here on this graph. Even though it went from being negative 1, 1 over here to 1, 4 over here, that's a difference of 3 units, like it's 3 units taller. That doesn't mean anything. We're looking at factors. Remember, if we're stretching by a factor of something, which means we're multiplying by something. So how did I get from my output being 1 to 4? Well, 1 times 4 is 4. So this was vertically stretched by a factor of 4. And so I'm just going to write that. Vertically stretched by a factor of 4. So now I have all of the transformations. That's going to give me, everything that I need. So then now I'm going to create my function. So my new function is, well, f prime of x. I keep missing something right now. Prime of x is going to equal negative 4 f of negative x. Remember, the negative on the outside represents the reflection over the x-axis. The 4 represents the vertical stretch, and the negative x represents the reflection over the y-axis. And that's how you do it. So the last thing that I need to teach you guys today is the difference between an even and odd function. And this doesn't have to do with exponents, like sometimes exponents help, but really if it's an even function, then what that means is that if you plug in negative f of negative x, it's going to be the same as f of x. So just f of x is equal to the same thing as f of negative x. Okay, and this really translates to it being symmetrical. It's a word I might not know how to spell. Symmetrical about the y-axis. Okay, so even functions are going to be symmetrical about the y-axis. This would be like a parabola, a quadratic function. Those are going to be symmetrical about the y-axis, the original parabola. The next one we're going to look at is odd functions. And a function, we say a function is odd if f of x, the original function, is the same thing as negative f of negative x. Just means that we can perform, oops, why is this so hard for me today? You know what, it's a stupid parenthesis right there. So basically if it's been reflected twice, it will still give you the same function. All right, and graphically what this looks like is that these are symmetrical about the origin. Why is it 2 right now? Okay, so we're just really quickly, this is only a couple of examples in your homework, but I do want to make sure you are able to tackle those. So if f of x is equal to x cubed plus 2x, we want to know, is this function even, odd, or neither? So really how we're going to do this is we just need to test. And we're going to make a note of that. So to test, see if f of negative x or negative f of negative x gives the original function. All we got to do. So let's check. Let's first check what f of negative x gives us. So f of negative x, if I plug, what this means, so right now I'm just trying to test it even. So this is the even test. So f of negative x is the same thing as, well, what I'm going to do is wherever I see an x, I'm going to just replace it with negative x. So this becomes, you know what, I need to use that stupid equation tool again. Sorry guys, it's such a gross color. Sorry. It's that or purple. And purple would throw me off. So this becomes negative x cubed plus 2 times negative x. Again, I'm just checking if when I simplify this, this is still f of x. Well, if I simplify it, I end up with negative x cubed minus 2x. And this is not the same as x cubed plus 2x. So since it's not the same, it is not even. So not even does not equal original function. All right, so failed the even test. Now we're going to check to see if it's odd. What do I want to do? The purple. All right, odd test. For the odd test, we're testing negative. Again, we're testing negative f of negative x. Okay, we're going to see what that is. So this time, what we're doing is we're going to put the negative on the outside, and then we're also going to make the x negative. So negative x cubed minus, well, here, we'll do plus 2 times, oh yeah, we'll do minus. We're going to do plus 2 times negative x, but that's just dumb. So plus 2 times negative x. All right. 2 minus x. All right, and then now simplifying it, well, this negative x becomes negative x cubed. This becomes negative 2x. Remember, when you have a double negative like that, it's going to be positive. So then I end up with x cubed plus 2x. So now this x cubed plus 2x is actually my original function. So since it's my original function, we are going to say that the function is odd. If it turned out that if they were not the same, then it's neither. It's neither odd nor even. So that is the original function. Function is odd. That's how we do it.